So hello and welcome back. Into the previous hour, what we saw was a neural network model that was called as a variable basis function network. And again, the general methodology in which we saw what was exactly similar, apart from some slight difference in methodology, a lot of difference into the conceptual level. But towards the end, we saw that it went up straight away onto the lines of how the multi-layer perceptron was. It also did the same thing as the multi-layer perceptron. It tried to regress a curve, it tried to find out a curve using a curve fitting approach. Of course, it was slightly more localized in nature, that we saw has its own advantages and disadvantages as well. But there exist some different kind of models towards a neural network. We will continue our discussion towards the different kinds of neural network models. And today, we will be taking in another very different kind of neural network model. Different because this time we are going to take a model from the classificatory class of models that are only applicable towards the classificatory problem. And this model that we take is known as learning vector quantization. Of course, as always, let us first stick into what the model name means. We will take it as inspiration, we will try to guess the network model, we will try to guess the concept, and later we will delve into the actual layer neural network architecture. So we say that it is something to do with vector quantization. What that means is that in this type of model, I will take in some vectors in my hand. I'll take in some kind of code book in my hand. I'll take in some prototypes in my hand, and all I'll do is that I'll apply a learning fundamental over these vectors. I'll apply learning over these code books. I'll apply some kind of learning over it. And when I say learning, from the past so many hours, whatever we are discussing, it has got nothing to do other than trying to make the model much better as per whatever data it is given to. Now we don't call it strictly as an optimization because the data given to might be new as per our expert system design. It might convey some new information, new meaning. The old one may need to be forgotten, the new ones may need to be remembered. So that's why we use an analogy of learning. But ultimately what I want to do is that I want to tune in these vectors, and that's what the whole model will be about. So that's probably what vector quantization is. The LVQ was called, and sometimes also called as learning vector quantization network, so the LVQN. So again, let us first draw the neural network architecture on the lines of multi-layer perceptron. So naturally some kind of inputs, some kind of outputs over here, and again I placed in a restriction that there would be a single hidden layer. So there is one input layer, there is one output layer, and there is one hidden layer. Of course, when I say the output layer, considering the fact that this is a classification model where the problem is to decide one out of the classes C1, C2 or Cn, why do I have n neurons over here? Why do I have n neurons over here? The thing is that each one of these neurons represent a class. Each one of these output neurons, they actually represent a class. Again, what happens is that because all of these, they represent a class, in this particular model that is already classificatory in nature, at any time one of these neurons is in an active state and all the other neurons will be in an inactive stage. So at any point of time, whenever I apply any form of input, only one of these neurons will have an active state, only one of these neurons will get excited, only one of these neurons will get activated, whereas all the other neurons that exist will be in inactive state, and whichever neuron gets activated, I will return the particular output of the class. So let's say this was a scenario over here. This will give me an output of 0, this will give me an output 0, this will give me an output 0, this will give me an output 1. So one of the neurons give me output 1 and all the other strictly give me an output 0. If it was a single classificatory problem where the inputs, they strictly belong to one of these classes, it will give me in this manner. If it's a multi-classificatory problem where input can belong to multiple classes, obviously there will be multiple neurons that will be activated, and those active ones will be the classes to which the input belongs. And of course we might have some connections out over here in this format. So again, this is the kind of basic network architecture that exists. Let me again draw these connections. Each one of these will have a weight of 0 or 1. So any weight from the hidden layer to the output layer will be strictly a 0 or 1. Normally we say that any weight of 0 can be said that the neural network is disconnected. That is even sometimes in the multi-layer perceptron. If a weight is fixed 0 and it cannot change at all, it is not allowed to change, we simply drop that connections. So let me say that similar to the radial basis function network, if the input was I1, I2, I3 and up till In, let's say all these neurons are nothing but vectors. Now remember, the word was vector quantization. So as was the case with the radial basis function network, all of these are nothing but vectors. D1 is a vector, D2 is a vector, D3 is a vector, Dp is a vector. And the performance is similar. There is an information gathering stage and there is an activation function stage. For the information gathering, they would behave exactly similar to the radial basis function network, where every di it calculates the norm of the applied input, say I, where I is nothing but I1, I2 up till In with itself. So this will be I minus D1, this will be I minus D2, this will be I minus D3, and so on. This will be I minus dp. So each one of these, what it's trying to do, basically it's trying to calculate the norm of the vector with itself. The I will calculate the norm of the input with itself, the 2 will calculate the vector with itself. So any general, let me say the I, the first thing that it does is it says what is the norm of the input with me. This is what information will further proceed. The next thing we know is called as the activation function that is to be applied as per this neural network methodology. It is the activation function that is to be applied. For some time, let me assume that the activation function input is called as yi. That goes towards the ith data center, let me assume that is given by the symbol yi. Now the activation function, let me say, is f of yi, which happens to be the output that the ith neuron gives. As per this model of the learning vector quantization, my activation function will give an activation value of 1 or an activation value of 0. It can give me only an activation value of 1 or an activation value of 0. It gives me an activation value of 1 if yi is the less of all norms over here. So let me say it gives an activation of value of 1 if yi is less than yj for all j not equal to I, and it gives 0 otherwise. So basically what happens is each one of these calculated some y1 over here, y2 over here, y3 over here, yp over here. It will be for all j not equal to I. So now what the network does at this stage, over here, every neuron knows all the yi's. I select the least output, I select the least yi, I select the least value of y over all these given yi's. So it's like different kind of neurons over here. I say that the different kinds of neurons that exist right over here, each one of them has got a Euclidean norm that it calculates. Each one of them has a Euclidean norm taken from the input that it has already calculated. Out of all these neurons, I state that only one of these neurons would be active. I state that only one of these neurons need to be activated, all the others will be deactivated. So I have a chance only to activate one of these neurons, and how that selection of activation is made by this activation function, how that selection of activation is made is that only that neuron that has the least distance from the input that gets activated. So towards the end, let's say this was a neuron that had the least distance from the neuron, it had the least value of yi. This gets activated. If I say this gets activated, this returns a 1 over here and all the others return a 0 over here as the outputs. So towards the end, only one neuron of this entire stage is active. Now remember, it's based on the norms. So what is ultimately happening is that the neuron that is as close as possible to the input, a neuron that is as close as possible to the applied input, that is getting activated, and all the other neurons are not activated. All the other neurons are not activated. In fact, that is called as a winner-takes-all approach. This is what we refer to as the winner-takes-all. The winner-takes-all approach would state that only one of the neurons would be activated and all the other neurons would be deactivated. There would be a competition among neurons to get activated, and the neuron having the least distance from the input ultimately wins. So there is one neuron that has already won, and from this there is a simple weighted addition, there is a simple reversal that we to go from the hidden layer to the output layer. All the neurons to which it is connected will get activated. So let's say this neuron was connected to 3 classes. This gets activated, this gets activated, and this gets activated. All the others would get deactivated. This is in case when the problem was of multiple classes, where an input could belong to more than one classes, This is what will eventually happen out. Of course, again, that I am assuming that the zero connections are not done over here, because ultimately this gets an output 1. Anything multiplied by 0 will automatically be 0, so I do not assume these connections they exist. From a simple neural network design, you can find out that if a simple layer-wise processing is done, where these are taken as the weights as zeros and ones, and these are taken as the activation, this is what you will get. If the class was single classificatory in nature, if it was that the input can belong only one of the input classes, then I'll get a good little drawing over here. I'll get that all these neurons, they map to any one of these classes. This is the kind of drawing that will come out to be. This neuron is connected to this neuron is connected to this neuron is connected to this. So whenever this neuron gets activated, this is the class that will get activated. Whenever this neuron gets activated, this is the class that will get activated. Whenever this neuron gets activated, this class gets activated. This is in case that there is a single, this is in case when any output input can belong to any one of the outputs. This is what the map will come out to be. So based on this, let us try to further explore this kind of architecture. Let's further kind of explore what kind of architecture it is. Again, what we got is that whenever any input is applied, I can find out what the class is. Whenever any kind of input is applied, I can find out what is the class to which that input belongs to. I'll apply the input, I'll calculate all the norms using winner takes all, I'll activate one of the neurons and whatever class it corresponds to, that will be declared as the winner. So let me draw in after this time what I refer to as the classificatory space. So these are some input I1, these are some input I2 and various classes drawn over here. Let me say this was my first class, let me say this was where my second class was found. Let me say this was where my third class is to be found. And of course they are intermingling with each other. I don't know whether I can ideally frame in a vision boundary, but the vision boundary would ideally come out to be like this. For this class it might come out to be like this, and of course something like this and something like this. These are more or less the idealistic vision boundaries that come out. It's only that whether we can form this kind of vision boundary or not in this entire space that has been given. Again, as it must be clear from the word vector, what I mean that these are points inside the space. While I was dealing with the RTFL also, what I did was that every neuron was plotted up over here as a data guide, as a data center. Similar terminology we use here. Any neuron, we'll draw it out over here. Let's say D1, I say this is D2, I say this is D3, I say this is D4, I say this is D5, I say this is D6, a D7, a D8, a D9, a D10 and a D11 over here. These are the data guides, the data centers, or in this case sometimes referred to as the subclasses as well. These are my training database. The LTQ has supervised learning only. So the thing is that whenever I apply an input I, let me say over here, all these data centers, they calculate their distances. So this distance will be calculated, this will be the distance calculated, this and this. And this was I. The neuron having the least distance wins. So in this case, D2 will win, that has the least distance. I kind of curve it up. I say D2 has one for this kind of input. All these data centers calculated their norms, the data being closest to the applied input, that always wins. Now for this point of time, I assume that all class they belong. In the RDFN, we had assumed that all the data centers know the kind of output that is located in that region. The same assumption I carry out over here. All the data centers, they know the class to which they belong or the kind of output that is prevalent in that region in which they are existing. So in this case, the output of any applied input I is affected only by one particular data center, only by one particular data guide, in this case D2. So I say I has exactly the same output as D2, or I has an output of O, which can be seen it is incorrect in this case. It was a hash, it is calculated out to be a D2. Now in RBFN, in a curve fitting approach, we were saying that the output is affected by multiple data centers to varying degree of extent. And it was important because we needed to capture trends, we needed to capture all these kind of lines. Here the problem is much more localized in nature, where you are only seeing your immediate neighbor and you are saying that whatever my neighbor is, I am exactly the same. So based on that, whenever an input comes, I can find out what the output would be. And when I say for any input that comes, for any configuration of the data points, I can find out what the point would be. I naturally mean that all these, this entire classificatory space can be plotted, and when I plot the classificatory space, I'll get some kind of decision boundary. It may be right or it may be wrong. That's all the difference that it takes from MLP to RDFN and RDFN to learning vector quantization over here. Now let me take in, now let me say that there is a training algorithm that we will be seeing later, which tries to place all these data points into the idealistic places. So it's natural that I'll have to move them up here and there. I'll have to do some kinds of things over there to move them up here and there. And based on that, I'll ultimately get in a kind of structure where all the data points are at the ideal locations for the best kind of decision boundaries to exist as per the limitations of this structure, as per the limitation of this algorithm. So some kind of decision boundaries are limited. In this scenario, I can say that any point lying till this place, it will be closer to D9. Once I move from here to here, it will get closer to D8. So this is a point of the decision boundary. And similarly, I can plot a decision boundary right between these three. Here, it gets between D7. So it will extend up till here, it will extend up till here, and this is approximately how the decision boundary can be formed. Now there is a concept of class and there is a concept of subclass. What D2 represents is called as a subclass. I state that this is the region in which the input belongs and D2 gets activated. As you can see, in this entire region, D2 is the closest. Once it gets here, D6 gets close. Once it gets here, D5 gets closer. Once it gets, it's approximately here, D3 gets closer to this. And therefore, there is a region in which the input comes. D2 is bound to be the class. In fact, as per present scenario, this entire region will be the subclass of D2. So that's what is known as a subclass. The entire region in classificatory map over which DI wins, the entire region over which DI wins is called as the subclass of DI. The entire class, the entire space in this classificatory space over which any neuron wins, it's called as its subclass. A neuron, for that sake, is called as a subclass itself. So what do? I take in any input, I see what is the region in which D2 is winning, and I plot this region up known as a subclass, a combination of various subclasses that belong to the same class. Now remember, in this case, D2 belongs to class O, D6 belongs to class O, D4 belongs to class O, D5 belongs to class O, D3 belongs to class O. So basically my class O is given by D2, D4, D6, D5 and D3. So a combination of all these subclasses is what my main class O is. and that is what's known as a class. So this entire region will be known as a class, and this entire region will be known as a subclass. So basic methodology, the entire region in the input space as per any configuration of the learning vector quantization network, or as per any configuration of the data centers over here, whenever a class di, wherever a neuron d wins, I say it is known as a subclass. That is the region in which the neuron d dominates, and all the neurons that belong to the same class, they denote the entire class. So there is a subclass or the subregion in the input space, in the classificatory space, where a neuron is dominant, and there is this entire space that comprises of multiple such points. And so what do we do when we train the neural network, when we train the learning vector quantization? What do we basically do is that firstly we can move these points around in this input space. So we can change D1, D2, D3, D4, D5, D6. All of these we can move them inside the input space over here. What additionally we can do is that we say that D7 does not belong to class hash, it belongs to class 7 belongs to class star, D9 belongs to class O. We can change their classes. So these are the two things that we can do as when we are dealing with this classificatory space. In that neural network architecture that I do, it can be easily said that every neuron of the hidden layer is subclass, every neuron of the output layer is naturally a class. I can change the position of the vectors of the neurons in the hidden layer. That will change my subclasses, that will change my centers here, or I can change the weights from the hidden layer to the output layer, that will change these classes. So from this we straight away move upon to the term known as training. Here I will be making use of a theory, I will be making use of postulates that's known as the Hedge postulates. I'll say that it basically states that if there is an axon A and an axon B, and this continuously tries to excite axon A, continuously tries to excite the axon B, both of them get modified, and axon B ultimately develops some kind of characteristics that is induced by axon A, that will ultimately get excited as per axon A if continuously the reinforcement is applied from the axon A to the axon B. So I will use some kind of same fundamental in trying to find out the data centers and the classes. Now whenever I refer to training, I refer to both how is it that we need to fix the data centers and how is it that we need to fix their classes. So there are two kinds of problems. Let me deal up with the second problem first, in how do I find out the classes. And how do I find out the zero vector weight over here? So there was this kind of architecture over here of a neural network, and these were these classes here. How do I find out this neuron belongs to this class, this neuron belongs to this class, or this neuron belongs to this class over here? How is it that the distribution of the classes needs to be done? Again, assuming that any neuron can be connected to a single output class, I think the class model that we had was that every neuron maps only one of the output classes. If it's a multiple model, then all the multiple connections might exist. At any given point of time, let me say even at the initial, there will be some positions of time in which they will be located. What I have in addition with me is a lot of training data with me, in which all these DIs are randomly located. And based on that, of course, I have to find out what the neurons are. Now, whenever I apply any kind of input over here, I get one of the classes as my output. I get one of the classes as my output. So there will be one neuron that will get excited over here, and there will be one neuron that will get excited up over here. There will be exactly one neuron excited over here, there will be exactly one neuron excited over here. So basically try to map any kind of inputs to any kind of hidden layer neuron to the output layer neuron. It can be done in multiple ways. Either it is that I fix the kind of neurons per classes, so I kind of fix that what neurons will get mapped, what neurons this way, that some kind of randomness, randomly in nature. Or I can have an initial clustering. I can find out where the data centers would normally lie, and then I try to heuristically attach these neurons into these clusters. So anyways, I can basically do a mapping of the neurons from the hidden layer to the output layer. So whenever I apply any kind of input, I see what neuron is activated over here, what neuron is activated over here, and if these two neurons are activated, I simply connect this. I simply say this neuron belongs to clusters. So for any other time, if this neuron, I apply an input, there's a neuron that maps up over here, there's a neuron that gets activated over here, I can say this belongs to clusters, and then I can draw a connection out this. When I say I'm drawing this connection out this, it naturally means I'm deleting this connection, I'm deleting this connection. The other part of it, if this weight, if I have a mechanism to learn this weight, then I need a mechanism to learn this weight as well. So there is W2 can be learned. So how do I learn W1? For this, I use the Heath postulates. I say whenever I apply an input I get my output O depending on whatever happens inside this neural network. I get my output O. Now this is a supervised learning, so I already have a target T with me. Because I already have a target T with me, I see if O and T match. I basically see if O and T match. Now in case O and T match, that is the output is correctly mapped, what I need to do is that I need to move the winning neuron. Now whenever I say that I apply this kind of function, I know that there must be a neuron that must have been activated in this hidden layer, and there must have been exactly one neuron. Let's say the I that was activated neuron. So let me say this produces the I as the activated neuron. If the output is correct, I basically need to pull the I towards I, because it's a classificative problem. I know that I represents some characteristics that the I should possess, so I try to pull out the I towards the I. So I say that my new value of the I will be some old value of the I plus, let me have some learning rate times how much I is different from di. So that is what my learning rule says. So every input tries to induce some of its characteristics towards its winning neuron. Every input tries to introduce some kind of learning characteristics towards its winning neuron. This was in case my output was correctly mapped. So if my output is correctly mapped, my input is trying to introduce some of its characteristics towards this neuron. Alpha T is called as the learning rate. If this learning rate is 1, then you can see this di and di will cut, and di t plus 1 will become exactly equal to I. It will, the applied input, it will make the input di exactly the same. If my alpha reduces to 0, there will be no effect of this induction, there will be 0 induction at all, and there will be no change in weight. But in case they are not equal, I say that apply the induction, try to affect the neuron but in the opposite direction. So this was when I said that an input said that I am exactly as you are, that I am exactly as you want to be, so have some of my characteristics upon you. This is what says that we two are different. I says to D that basically there is a difference over here, that I do not possess the characteristics that you should ideally be possessing, so please move out of me. Again, as it can be seen, alpha is a learning rate over here. Now, learning rate normally we reduce with time. So as time increases, normally we would reduce the learning rate by some amount, let me say by a function g of alpha t, where g is a decreasing function. We slowly and slowly reduce the learning rate with time. And why do we do that? Because initially all the data centers, initially all the data types are random nature. So whatever input is applied, it only knows its output. And input only knows its output, so it's better to learn from the input a lot. Every data center is random in nature. So whenever an input comes, it tries to learn as much as possible from it. Towards the end, we know that the data can be noisy, a coming input can be noisy, and all DIs have become mature over now. They have become mature over now. They have already retained the characteristics that they should ideally be retaining from all the various inputs that were applied multiple times over the past. Towards the end, they become all mature in nature, so therefore there is less to learn towards the end. So therefore we normally reduce the alpha learning rate along with time. This is the basic learning algorithm that is known as an LVQ1 algorithm. So let us see what exactly happens into the classification, into the classificatory space. Let me say I2 plot 2, I1, I2, and there are some things over here, there are some pluses over here. This is the training data that I have got. Let me say there was a D1 over here, there was a D2 over here, there was a D3 over here, there was a D4 over here, there was a D5 over here. So when this input comes, it tries to pull it up a little towards its side. When this input comes, it tries to pull it up a little towards its side. When this input comes, it tries to put it up a little towards its side. This is the winning neuron, and so on. And as it can be seen how the weights are decided between the hidden layer to the output layer, because by seeing I can see whatever neuron one, it must belong to the same kind of output class. Later on what happens is that this is exactly what happens after one iteration. So my D1 has moved from here to here. My D2 has gone up a little towards the mean of these two. They started coming in. Next time again these two will pull. Each one of these inputs will pull it up a little towards the side. Of course the pull will return because alpha has reduced. So they will migrate a little more towards inside. And all these, this will pull this inside, this will pull this inside. So what happens is that whenever I iterated over all the inputs I, in my historical database, every input, either be it this, either be it this, either be it this, every input in the training database, what it does is that it tries to attract the nearest data center towards itself. And as a result of multiplicative attractions, every data center, it tries to come deep inside the class to which it belongs. So might be towards the end I'll get D1 over here, I'll get D2 over here, I'll get D3 over here, and I'll get D4 over here. After that, this will attract this over here, after this will attract this over here, this will attract this over here, and it might be in an equilibrium state, something like this. So this was attracting it over here, this was attracting it over here, this was attracting it over here, and might be this was attracting it over here. So there's no kind of attraction net that is available. So every input is trying to introduce some characteristics similar to what I said was the axon theory, where every input tries to attract out the other, where an axon tries to attract the other axon. There is a slight problem with this learning vector quantization LVQ learning algorithm 1. That is what we try to introduce out, we try to remove it towards the next algorithm that we built for the learning vector quantization. That will be LVQ2 that we study out here. any neuron input tries to attract out any neuron, and sometimes this can be massive in nature. The attraction can be massive in nature. So what we do out here in this LVQ2, we go up exactly on the same lines. However, we find out two things. Whenever an input is applied, we find out, and this is the output that is produced, we find out J, the winning neuron, as was the case with as was exactly the case in our previous approach where we found out what the winning neuron is. We try to find out what is who is it that wins, and we find out K, the first losing neuron. We find out that who won and who lost. Out of all those neurons, we find out who was the closest winning neuron, that is a neuron that lies at the closest center, and who was the closest losing neuron. Again, that we match if basically the output and the targets are equal. So what do we need to do? We additionally secure one thing. We find out, suppose in a space, this is where the winning neuron was found, so the neuron J, and this is where the losing neuron was found, so let us find out K. We try to ensure that the applied input does not lie up somewhere like this, in the middle sense of these two. So there is a window that is constructed out here. Let me say a window of length W that is constructed out over here. We find out whether this condition is true. Let me say the J is nothing but the distance of the winning neuron to the applied input. So DJ will be basically equal to the input minus the center number. Okay, I have to take this DJ, I have to take this DK. Let me take up F. I only used F. Let me say LK is the distance between the input and the distance vector, and let me say that LK is nothing but the norm between the input and the applied distance vector K. So I am measuring these two kind of distances from the input. So I measure whether dj upon dk. I am measuring for a central tendency over here in which a neuron input tries to lie somewhere right between these two neurons. Is less than some threshold that is defined. The threshold is defined by the window length over here. That will decide how close I am to the input. If this is true, then basically I need to pull the input, I need to pull the neuron J towards the input, and I need to push the neuron K outside the input. So there are two things that I am doing here. I am trying to make the input network as close as possible. I am trying to attract the winning neuron, and I am trying to repel the losing neuron. There are two things that I am trying to do in this algorithm LVQ2. I am trying to attract the winning neuron, I am trying to repel the losing neuron. So basically what happens is something that is very simple. What happens is only that my dj mu, this is what I need to attract. It will follow the same equation. In addition, my dk has to repel. So there will be some minus alpha t into input minus d. So this is trying to induce, the input is trying to induce its effect on dj over here, and input is trying to go away to de-induce its effect over dk. dk is trying to pull itself out, and dj is trying to attract itself towards the input. And again the learning rate comes into the picture. So this is what the modification we make to the LVQ2 algorithm. So basically, in this manner, you can always classify a model. We have built in a classificatory model where any input, using this code book, it's sometimes even known as a code book vector because the list of neurons is nothing but like a known set of inputs and outputs. So whenever the input comes, I can find out the best the knowledge base that I've got, I find out the best known inputs, and based on that I give it the corresponding output. And I use an intention technique because my database has been reduced to a much smaller size of knowledge base. Normally it would happen that we see the training data set, we try to find out in what proportion the various classes are found, and in similar proportion the subclasses are divided into the classes. Now remember, there is again an interesting thing that how many subclasses per class would be there, and how many neurons of the hidden layer would map to how many would map to one neuron of the output layer. That's again based on the model that we got. If I have somehow got in kind of data that they are 80% references of class A and then 20% references of class B, might be I use 80% of the hidden layer neurons to cater to serve as a subclass of class A and 20% to subclass of class B. So there are numerous things that you can do. Again, this might not be optimal. My data might be highly redundant, the class A would be very close to each other, class B would be very far apart from each other. It might be possible that the scenario was something like this over class A and it was something like this over class B. So even might be if I place in a single neuron over here, it will be able to dominate this entire region, and for this I might require a number of neurons over here to cater to this region and to this region, and then is when I'll get in a better classification model. So nothing like I said, optimally you cannot determine, but then again you require some kind of heuristic so that you can find out all these things. The next model of study that is quite similar to in nature, except for one small difference, except for only one small difference, is called as a self-organizing map. That is what is known as self-organizing map. Again, a three-layer architecture. So there is a hidden layer and there are some output layer. The only difference is that learning vector quantization operates in a supervised mode, whereas self-organizing map they operate on an unsupervised mode. Here also each neuron is a center, let's say D1, it's D2, it's D3, it's Dn, and it's C1 over here, it's class 2 over here, it's something like class 3 over here. And input is applied over here and there's some kind of output. So if it's from supervised I'm going to unsupervised, what I need to change is the basic training algorithm. That is what it takes. But then if I only take it supervised or unsupervised variable as self-organizing maps, now that is because of two things. That is, as it is named from the name, self-organizing, that means they organize themselves up to apply the input, they organize themselves up accordingly, what we would be seeing very close. And then it's a map. It's map because this hidden layer is nothing but a collection of neurons that are arranged in this kind of structure. This is what is known as a self-organizing feature map. It is known as a self-organizing feature map. Of course, it may not be in this manner, of course, n cross n. It can be in form of hexagon rings, it can be in form of linear structures, it can be a three-dimensional map. So we got a very generalized meaning of the word map, but then what it means is that there will be some kind of structure. What we would be dealing with is only this m cross n map out over here. Now why is it called as a feature map? What the basic intention is that if my entire classification space where I had I1 and I2 and it had a dimensionality of n, can I reduce this into a 2 by into an m cross n matrix that has a dimensionality of 2? So I'll be basically typecasting in this entire algorithm that we see. What we realize towards the end, that we try to typecast this highly dimensional space over a two-dimensional map, and that is what the word feature comes in. We've already discussed this was known as a feature space. A feature space of n-dimensional when typecasted, when mounted over a map of two-dimensional, and that's why it will be known as a self-organizing feature map. Now we are a little more into where we can understand the self-organizing part of it. The self-organizing part of it means that towards the end of training, all these neurons, they naturally mean a class. They naturally correspond to a class. Any neuron over here, as per our learning of the learning vector quantization, means a class. So let me say they were classes A, B and C. Towards the end, this is what would happen. It is known as self-organizing because the class A will separate itself as a distinct feature of this map, class B will separate out itself as another distinct feature of this map, and class C will separate out as a separate feature of this map. How we of course see it towards later parts of this time, but what is intended as of now is to understand it is a self-organizing map. So based on the same architecture as the MPQ, using an unsupervised approach, we need to typecast a high dimensional space into a low dimensional space, and self-organizing because all these neurons may initially belong to different classes, they may belong to different areas, but towards the end what we will see is that all these neurons, they arrange themselves in such a manner such that all the classes, they happen to be distinct. And by the way, this is exactly what happened into my feature space. All the classes were distinctive to each other. So here is what I get, another motivation, that the only difference between a feature map and a feature space is that the spaces have all been removed by some intention technique. The spaces have been reduced and there is some kind of typecasting that has been done. Else this view and this view are quite similar in nature. Of course, this is a very high dimensional view. So you will have to consider all those things when you consider the statement that these two views are exactly similar to each other. The mathematics of it is again exactly similar as was the case with vector quantization. I have an input I. What di does is that it tries to find its distance towards the input. It tries to produce an output. OI, there is a winner takes all approach. So f of yi, the activation function or the final output activated neuron, is basically equal to 1 or 0. 1 if yi is less than yj for all I not for all k not equal to j, 0 otherwise. So it's exactly the same where one of these neurons gets activated and ultimately activates its corresponding class. The entire mathematics is the same. What I need to do here, I just need to frame in a training algorithm that is able to do this. If you look at the space, you can again consider the space where the various di's would be located. And I need to just arrange them up in some manner, in an unsupervised manner. So for now, I've got some inputs, I've got some outputs, I've got the framework. The only thing to discuss is the training algorithm that will make this possible. The only thing to discuss is a training algorithm that operates in an unsupervised mode. Now into the entire one, the training algorithm, it is natural that they behave similar in this kind of feature space. We'll see how this operates in kind of feature map. Now in order to understand how this thing proceeds in a feature map, we'll introduce the term known as a neighborhood. Neighborhood is nothing but all the neighboring neurons inside a feature map. Now this feature map, if it's a two-dimensional map, it's a circle. For three-dimensional map, it will be a sphere, and all the higher dimensional and the lower dimensional as it is. A feature map will always have a radius r. It will always contain a definite number of neurons inside itself. That is what will be known as a neighborhood. So we go away with this, we go away with this. What we are to do, we are to find out a learning algorithm for this purpose. The learning again is based on the Behet's postulates. The learning is exactly based upon the Behet's postulates. I apply the input I get an output O, and I get J, the winning neuron. I get J, the winning neuron. I find out the neighborhood of J. So that will be, let me say that is equal to NdJ. The only change with derivative quantization is in place of modifying the neuron. Of course, I do not have the target with me, so I can never say anything. The only thing that I will do is try with this input, assuming the output to be correct, I will put up the winning neuron. The only thing is that in place of inducing effects or in place of putting only the winning neuron, I need to pull up this entire set of neuron Nj. If this is the winning neuron, my Nj is all these neurons. It's the set of all these neurons. So basically, I say that my dj is not at a time t plus 1 is nothing but my dj at time t plus alpha times input minus dj at time t. I say this is alpha t, where alpha t would be replaced by the term ht over here. As we move away from the winning neuron, the effect of learning should decrease. So basically, as I go away, the input that comes in, it pulls the winning neuron heavily. It pulls in the winning neuron heavily, and the other neuron, as we go above, we have to pull in that heavily. Because the input line goes in, that is exactly the winning neuron. That is a neuron that should possess exactly the same characteristics as the input. The other neurons may belong to different classes, so it would be bad idea to pull them out. Another point is that if you very badly pull in the faraway neurons, the entire feature map would try to contract. The entire, this entire space would try to contract, and that is not what we want. That all neurons line up as a bunch together towards the center around where the majority of the inputs are. So as we go about in this feature map, as we go about in this space, the effect of ht should reduce. So we say that ht has to be proportional to r. What we take is that ht equals to alpha t into e raised to power minus the difference between the neurons. So let me say that the dj was the winning neuron. So I say it's the difference between dj minus dk. I'm iterating over the k neurons here, so I will replace it with by k. Square divided by 2 sigma t the whole square. There's an exponentially decay that I have assumed up over here. There's an exponential decay that I have kind of assumed over here. And when I say it's dk, what I mean basically, k is a member of neighborhood of j, and my alpha t again is the learning rate, and alpha t would naturally reduce along with time as per exactly are dealing with the previous algorithm that was in learning vector quantization. So that was exactly how the learning rate needs to reduce. The same motivation lies up over here. So there is a simple fundamental that I apply the input, calculate the output. Once I know the output, I calculate what is the neighborhood of it. I calculate the entire set of neighborhood using this neighborhood function. The neighborhood function will return me a set of all neurons that lie close to it, including this neuron. I will modify it by factor ht. With a multiplicative factor ht, it will move all the neurons within this moving set of neurons. So let me say this was where the input lied. It will like to move all the neurons, and as we move away from the winning neuron, the effect of it would reduce. So that's why I have multiplicative term ht over here, and ht I have reduced it up exponentially. So based on whatever is the difference with dj, it reduces up exponentially over here, multiplied by the learning rate. And with this learning, we'll see into the later session, we'll see into the next hour, how is it that it affects the self-organizing feature map, and why is it that it is self-organizing in nature, how is this map arranged. That is what we'll see into the next lecture, along with of course